I'm going to tell you a little bit about the Advanced Quantum Test Bed, where I am the head of hardware. Yes, please. Thank you, Travis. The center is directed by Professor Irfan Siddiqui of UC Berkeley and Lawrence Berkeley National Lab. It is one of 2 US Department of Energy quantum test beds, the other one being QScout based on trapped ions. We are a superconducting platform. Our mission is to develop and deploy an advanced full-stack superconducting platform for quantum computation and make it available to users from across the community, from academia, national labs, and industry for deep collaborative research projects, and in the process to train the workforce of the future. And all of this is done in a synergistic mode with other solutions available on the market for experimental quantum computing. So some descriptors for the work that we do. We have a unique quantum platform with deep user collaboration involved in broad exploration of technology while developing future QIS experts. So what all of that means is we have unique advantages, not just across the technology platform in terms of our QPU architecture, our gate development, cryogenics, and room temperature electronics for control, but also in the way we use this to engage in broad exploration of technology. We do not use our resources to just scale up and engineer to arrive at larger qubit numbers for our algorithms in that way. Instead, we devote our resources to explore the fundamental science and technology at the smaller numbers that will pave the path to future generations of processors and algorithms. And starting with the quantum processors, this is done in synergy with some work done at UC Berkeley, where we have also efforts towards novel qubits, including fluxonium and Kirkas and other types of novel superconducting qubits. Our quantum processors presently are made up of transmons of varying architectures. In particular, the Trailblazer chip that we've been using over the last few years for simulations of physics and chemistry, I have some of the numbers for qubit gate fidelities, single qubit and 2 qubit gate fidelities, state of the art in the 99.8 and at bare minimum to 99.95 for both single and 2 qubit gate fidelities. And in particular, I'd like to highlight one of the unique resources that we have is a single-step 3-qubit itophily gate with 98% fidelity. That is not found on any other platform, as far as I'm aware. The exploration of processor architectures. What interests us partly is we don't believe that the final optimal path to having the perfect processor is yet known. And so we do explore this phase space, going from highly coherent, hardware efficient processors with fixed frequency transmons and fixed coupling, so that's our Trailblazer chip, all the way up to SpiderNet, which is a 3D integrated quantum processor, enabling up to all-to-all engineered entanglement of qubits that has been under development for the last 2 years. And this is highly connected and highly reconfigurable. And then we have a number of other processors in between, and you see some images of the prototypes for these processors here. And this enables us both to have a varying range of processors to match with different experiments, but also to help us iterate and arrive at our next generation of processors longer term. Then higher up, we have our cryogenic platform. We have access to a number of cryostats. One example that showcases the effort is what we call Blizzard, which is a Blue Force XLD series fridge with 160 lines, RF lines. And what is different between, so in industry, the same size fridge would be used to run a 50 qubit or 100 qubit processor. And in our case, we would like to use a resource like this to enable parallel experiments at the same time. And so we've worked with, we've partnered with a company called Bleximo at Berkeley for design and implementation of a cold stage that is seen here. that compartmentalizes and partitions the experimental space under the base plate to enable thermalization, routing, and shielding and to accommodate at least 4, sometimes up to 8 experiments at the same time. So this has been a very fruitful collaboration, and it has worked really well. And we always have this running 95% of the time it's on with a number of experiments in parallel with varying architectures and processors. Outside the fridge, on the room temperature electronics side, we have 2 sets of solutions. The standard control stack that we have available for user experiments, we have partnered with Zurich Instruments for this for the last 3 years or so. And we've worked very closely with them to develop features at the firmware level all the way up to software. And this has enabled us to make the system a lot more efficient for our experiments with fast parameter change without the need to recompile and re-upload every time you change a parameter in the circuit. And also deeper access to FPGA level functionalities to allow custom feedback experiments. In general, Zurich Instruments scientists and engineers work closely with us to accommodate the custom needs of users. So if we receive a project, a proposal from a user that has scientific merit and could be done on this control stack, we will make it happen. For even deeper access and modularity and extensibility, we have our own in-house control solution called QuIST that has been under development at Berkeley Lab for the last 4 or 5 years. This is really a testbed for controls. It starts up from the FPGA layer all the way up to gateware and firmware and software. We have had a part of our team, FPGA experts who have been chief architects of this. It is completely open source. To our knowledge, this is the first published open sourced control system for superconducting quantum computing. We've been testing this and on all sorts of different experiments. Aside from the control system itself, our team has also developed mixing modules for RF mixing that basically integrates the amplifiers and mixers and filters everything into a very compact, energy efficient and space efficient PCB. This has also been published and open sourced. We've actually had people from universities reach out to us, and we give access to our repo to everyone, and they can basically have this fabricated for themselves, reduces cost by a factor of 10 compared to putting together a discrete chain. And altogether, the system has been tested with characterization protocols, and it works. Basically, we get comparable results with industrial solutions on this. The team that has been developing this, one of the advantages of having a center like the Advanced Quantum Testbed is that the control development team is co-located with the experimental team. And so we have our engineers and scientists working together, and our architects who developed the control system also worked on quantum measurement and applied their system to develop automated gate calibration protocols, including two-qubit gate calibrations. This is usually a resource-intensive effort that takes a lot of time if done by hand, which is how most people do it. And we've done it automatically. We get comparable fidelities at the end much more quickly, and this has also been published. I should mention that, this work has been under development for a few years now. We're now porting it to 3rd generation RF-SoC boards, and that will increase the functionality and also drive down the cost even further to be an order of magnitude lower than industrial solutions per channel. So we believe that this will, in the long term, lower the barrier to entry for junior academic groups who are trying to get started in experimental quantum information science. So the full stack is kind of tied together by our software stack called Qtrol. This is what the system integration looks like. The user can submit circuits generated by any of a number of openly available resources. As long as the circuit is in the OpenQASM format, we have a transpiler that works together with a number of optimization protocols that we have. Some of these are also open source tools developed at Berkeley Lab, such as the Berkeley Quantum Synthesis Toolkit, BixKit, where you just give an error threshold, and based on that, the tool reduces the size of the circuit in both depth and width to bring more complicated circuits within the reach of existing NISC hardware and processors. And so all of this is kind of tied together, and the pulses are generated then to run on the control hardware. And so once you have all of this full stack at your disposal and you can modify it at will, then you can tackle any number of challenges in the scientific landscape. Some of the areas that we have been engaged in the last few years can be broadly classified into these three categories. It's not comprehensive, but a good way to look at it. Quantum characterization, verification, and validation involving error characterization, noise tailoring, error mitigation. We've been doing a lot of work on novel quantum control. Aside from the control electronics, this is work such as multi-qubit gates, ternary quantum logic, so higher order. So we have an active QTRIT program as well. We've done information scrambling of black holes on QTRITs just to show the power of higher order logic and compilation. And then these tools, of course, build on top of each other, and then you can apply all of this to do quantum simulation of physics and chemistry. And then you will get, once you mitigate and once you understand your noises and errors and mitigate them and can control things at will, then you can, that enables you to do much more powerful simulations, even on more limited systems that we have nowadays. So that describes roughly what we have. What do we do with it? We use it, of course, for internal research, but also we make this available through in the framework of the user program that we have. So this has opened up over the last 2 to 3 years, and we have a call for proposal once a year, but we also do accept proposals on a rolling basis throughout the year as well, and then put them in the queue. So the way this works is everything is laid out on our website. The initial step is just a letter of intent. Takes just a few minutes to fill this out, a couple of paragraphs. And that goes through an internal staff screening. And the projects that broadly fit our direction and our resources are then invited to submit a full proposal. And that is, again, it's just a couple of pages. It's not too complicated. And that goes through an expert review process, both internal and external reviewers. And then the projects are accepted. And this process is designed to be open. Our staff is in communication with the proposing team throughout the process. What we find is that a lot of times the scope of the project has to be collaboratively designed together, even though the initial idea comes from the proposing team, to make it amenable to the stack as we run it. We really work collaboratively together. There's no other way around it. One thing I should mention is that we do want to take advantage of the full stack that we have and the way we give access to every part of the stack to the users. So if a proposed experiment is basically just a circuit to be run, that can be done on any number of cloud solutions. So that typically is not what we're aiming at. We're working synergistically with other solutions that exist. So our value is, of course, the deep access that we allow both to the resources, to the full stack, but also to our scientific staff. So the project needs to basically be complex enough to require those resources. And these are just a few project areas, everything from superconducting quantum processor architectures to quantum characterization protocols. We're wide open. Anything that has scientific merit that requires any part of the stack, we work with that. And the lifetime of the project, once it's accepted, there's scoping that always needs to be, this is done in an agile way. Things evolve fast and need to be adjusted. The projects are put in a queue and they're executed as resources become available. And throughout the execution process, which typically takes anywhere between 3 to 12 months, there are regular meetings with the two teams that are working collaboratively together. And then at the end of the day, this results in publications. An overview of some of the user institutions that we've had, color-coded to denote national labs, universities, and industry. we've received proposals and worked with people from all over the US. We are also open to international collaborations as well, though that has not happened so far. That is not a barrier. So in summary of our user program, we have an open quantum resource. Every part of it is open and accessible in every sense of the word. It's open source, but also openly accessible. We have full flexibility for the users. Exchange of best practices. So one thing that we've noticed is that there's this virtuous cycle that results from having a range of different user projects working together at the center, where things that are developed through one user project end up finding use in another user project. So for example, these QCVV tools and characterization and mitigation of errors that are developed as part of some user projects end up working well for to enable simulation, quantum simulation projects for another user. And sometimes we bring together our users in annual meetings and have them kind of talk to each other and learn from each other and exchange ideas. And that has been also a very fruitful result of basically serving as a nexus, as a hub to bring people together. And throughout all of this, we're actively developing the workforce. Our students and postdocs are deeply engaged in running these user projects, and they get publications out of it as well. And after graduation, they end up going to places like Google and IBM and Edison Bob and any number of places. Or they stay at Berkeley Lab or other national labs and become scientists. So I just have a couple of slides using a couple of user projects as context to talk about the modes in which our user framework enables the community. So this particular project was a quantum simulation project on nuclear spin dynamics. The proposing team was from Lawrence Livermore National Lab. And it's a hybrid algorithm problem. And when you run this algorithm naively, you get very noisy results that don't make sense and don't match your expectations. But we basically worked very closely with the proposing team to understand their needs and for them to understand the NISQ hardware limitations that basically everybody has, even with state-of-the-art fidelities, as I mentioned before. It's still not at a place where you can run some experiments that would be expected to be run in a few years from now, right? And so once you develop that mutual understanding, then you can match tools together to meet the needs of the algorithm as well as the hardware. And then at the end of the day, after weeks of very close collaboration, we were able to get really good results that would not have been possible without this deep access. So I would like to read this quote by a member of the team, Kyle Wendt from Livermore. There's a very clear vacuum in the scientific literature about nuclear physics on quantum computers, and the understanding of what's really going to happen on a quantum machine. AQT's main edge is the intimate access we have with the staff to understand how our simulations are running and what's happening. This access is not available anywhere else, and it helps us try to best tune our work to that platform to maximize our success. And so that was an example of how the deep engagement between the two teams results in scientific impact. So moving on from the national lab landscape to industry, we've worked with a number of industrial partners, but also we've had industrial companies apply to be users at our facility. So an example here is by, we've done a number of projects with Quantum Benchmark, centered around characterization and mitigation of sources of noise and error. And we have an example of it was the first experimental demonstration of randomized compiling for twirling noise. And on top of that, there was another project that added to that. This results in significant improvements on existing hardware. So Joel Emerson says, AQT helps us test our tools to understand how to improve the performance of our software solutions and understand end users' pain points. As a result of the collaborative work between our site team of scientists and engineers and those at AQT, we can develop better and more reliable tools for this purpose in the design stage and during the runtime stage when we're running our applications. So this turned into a product that Quantum Benchmark offers. Later on, Quantum Benchmark was acquired by Keysight. And now we actually, because all of this is governed under the terms of a CRADA agreement between the two teams, they retained the IP on this. And now we actually license this product from Keysight to help run the projects for our other users. One further example for this, earlier in the week, we saw a presentation by members of Supertech that was acquired by Cold Quanta later, and I believe it's called Inflection now. So we worked very closely with them on development of tools that allow pulse level optimizations to get the maximum performance out of existing hardware, doing hardware-aware compilation of these pulses for a given circuit. So you see some of the results here. And Pranav, the CEO of Supertech, his reflection on this collaboration was that what's unique about the opportunity to work with AQT as a user is to have access to the hardware properties that you wouldn't usually get from working elsewhere. At AQT, we're getting deep into discussions about how the hardware operates at the true fundamental physics levels. So basically, all of this goes to show the value you get from deep access to the full stack, every part of the full stack, and also to the scientific staff that we have. So this is something that is not, you can't gain this level of access and arrive at this level of scientific output and industrial output without working closely together. So, as I mentioned, all of this work is covered under the terms of agreements that are signed between the two teams. But at the end of the day, we would like to see publications come out of the work as well. And so over the last few years, as the user program has taken off, we've had a growing number of publications, and these are all joint because the projects are fully collaborative. So members of the proposing team as well as our team are jointly publish the results. And you see this growing trend here with the journal publications tracking the preprints. So we do have a website that has all of these details available. Please go to aqt.lbl.gov. You can submit your letters of intent there. And we also have a pretty nice virtual tour where you can actually take a tour of our lab and see what it looks like. We've been operating in COVID conditions, but as we're getting out of that, we would like to actually have our users come on site and work closely with us in person, if possible.